Excellent. Thanks, everyone. I think it's been a interesting but long day of exciting talks. We wanted to conclude the workshop with some thoughts on from a manufacturing and design perspective, where AI can play a part. How can we bring in more folks from materials manufacturing and design into using AI tools, and what are the bidirectional advances that we can focus on. So we have a stalwart set of panelists here. When I call out your names, if you'd be so kind as to show yourself on the screen here. So our wave, we have Olga Wodo from University of Buffalo. We have Mark Fuge from University of Maryland. We have Venkat Vishwanathan from Carnegie Mellon. We have Mike Salpukas from Raytheon, and we have David Tew from ARPA-E. Thank you all for being here. Appreciate you taking the time to be participating in this panel. A few points of etiquette. Please feel free to. I have a set of initial questions that I want to ask and get thoughts from the panelists. Feel free to include comments on the chat. I will moderate the chat, look at a couple of key questions that will help us keep the discussion going, and proceed with that. So first, opening statements. I'd appreciate a couple of opening statements from all of us. Could you discuss your perspective on research opportunities, and what are the challenges for AI in design and manufacturing? So let's start with perhaps Venkat.
All right, thanks, Bhaskar, and happy to be here in this great panel with a great group of people. So I think the challenge from my perspective is to try and build machine learning models that would give us the ability to understand residual physics that is not already captured by conventional physics-based models. And I think being able to automatically learn representations that allows us to capture this missing physics, I think that is the new exciting capability that I think is enabled. And associated with that, and I don't know if David Tew had this foresight when he named his program Differentiate, but the capabilities enabled by differentiable programming, I think, is going to be a fundamental game changer in the ability to do gradient-based optimization. So I think those are the two exciting avenues along which I think great progress can be made over the coming decades.
Thanks, Venkat. Olga?
Sure. Can you hear me? Thank you. So I will echo what we just heard in terms of representation and the importance on finding the robust representation that captures the physics. And I will give you the perspective from my own research, like in microstructure design or microstructure informatics. So we are also looking into robust representations that will balance the interpretability, dimensionality, ability to capture the correlations with the properties that we are interested in. And in my group, we work on questions that on several representations, like descriptor-based statistical functions like two-point correlation, topological representation. One thing that we found is that the physics or the expert, if we can enrich it in any representation, basically this gives you the most improvement in terms of machine learning models. And we see it across multiple different projects, not only the core like photovoltaics project, but also additive manufacturing. When we train the models for prediction of the temperature distribution, the moment we start like enriching our features with analytical terms from classic solutions, we start to see much faster convergence in terms of neural networks. So those are my two thoughts when it comes to the key challenges now. Like we need to enrich more expert knowledge in terms of like representations.
Awesome, thanks, Olga. Mike, you want to go give your perspective?
Sure. Thank you for having me. we are definitely interested in the physics-based models and sort of pulling out the physics and deterministic solution first, since those were discussed a lot. I'll bring up a couple of other points. One is definitely model drift over time, and this challenge where you start a manufacturing run and you don't have a lot of data in the beginning, but that's when the ROI is the greatest for finding a solution and deploying it. So you're always under this killer time pressure where when you have the least data, that's when it's the most worth it to come up with a solution. And then if you do have a solution that you have pre-ordered, how do you detect whether there's an anomaly or a change in the state that's causing that model to no longer be valid? The second big challenge is sort of the integration across the whole engineering lifecycle, where if something goes wrong in the field, you want to be able to trace it back through all of the fracas events, the maintenance that's gone on, the manufacturing, the supply chain design, all the way back through the requirements to figure out where in the process you went wrong. And a lot of people are sort of working on point solutions for each part of that, but pulling that chain together is quite difficult. And if you don't plan for it ahead of time, it's really almost impossible to sort of add after the fact.
Mark?
Sure. Can you guys hear me okay?
Yes.
Great. Awesome. Thank you so much again for the invitation and for assembling this wonderful group of people together. In terms of a sort of a general challenge, I guess I'll take a more sort of applications oriented viewpoint, which is that there's been a lot of promise in these kind of techniques. And I was sort of fortunate to enter when it was kind of the Wild West. And I feel like now we're at a point where we actually have to deliver value to people, whether that's, for a company or a research organization. And so I think some central challenges that we're going to face in this, and this may come up later in conversation, has been what are some of our key kind of challenge problems or driving statements, kind of like what's our self-driving car grand challenge, so to speak, for our community that's really going to spur value and investment beyond just myself sitting in my research lab or other research labs around that. That's much harder than it sounds. And an associated problem with that is, how do you measure success? Sort of metrics for that, because it's not going to be the same as the metrics for computer vision or natural language, although I think we'll learn a lot from those. So those to me, what are the challenge problems and data sets that are going to get us there? And then what are the metrics that we're going to use to really sell success are, I think, the two largest challenges, even though they're probably the least interesting or, elegant, but I think they're probably really important.
Awesome. So that's actually going to kick off a whole bunch of next questions. But Dev, you want to wrap up the perspectives? Yeah.
And you can hear me, I take it?
Yes.
Great. Well, thank you very much for the invitation. I appreciate it. And actually, my comments are somewhat along the lines of Mark's, and the fact that, within Differentiate, we're supporting 23 different teams to develop these different design tools, optimizers, surrogate models, generative models. And it's clear the ML methods work. I guess the question is, do they work well enough to justify the cost of training? In some cases, I think the answer is yes. In other cases, I'm not so sure. But then it comes down to, well, can we really do a better job kind of estimating or guessing at what the cost of developing these models is going to be, and how generalizable are they going to be once we have them? If I develop the ability to execute a design, if I'm going to execute the design tens, hundreds, thousands of times, it's kind of a no-brainer. Yes, the ML methods probably work. If I'm going to do it 1, 2, or 3 times before the constraints change, require me to retrain everything, is it worth the cost of training? And how transferable is that knowledge I've taken from, my current technology state into a state where the technologies may change and the constraints of my problem may change, requiring some retraining? So transferability, generalizability, I think, are kind of big questions, and developing some way to at least guesstimate what the cost of training might be up front, if we can do that.
Awesome. So takeaway from I'm just going to try to paraphrase this so that so there are one thing that seems to be overarching across this is, how do we capture the unknown unknowns, if you will, right? The residual physics, unknown unknowns. Then there is, what do we do in the face of uncertainty, right? So, and then third is, how do you generalize, and altogether, how do you add value, right? So that seems to be, and so let's hit those questions one after the other, right? So in terms of adding value, right, is there a North Star that we can use to guide this fundamental research? So perhaps are there specific sub-problems where we could invest in getting more data or getting benchmarks, having, like Mark said, can we define metrics? And this is, I mean, when I was listening into some of the, something that Olga organized a couple of weeks ago, one of the questions that came up was, do we in the material science community, perhaps in the manufacturing community, have a North Star, right? So is there, for instance, if you look at protein folding, or if you look at genetics, right? Genetics, there's a North Star, says, can we understand the rules of life? In astrophysics, can we understand how the universe was formed, right? So in materials and manufacturing, is there a North Star for us, right? So I'm going to let's again start with Venkat. Your thoughts on that?
Yeah, so yes, so I wrote this position piece, which I think puts two North Star problems in materials and I think engineering. And I think along the same lines, right, it has to be ambitious enough, right? And I think we already, I guess, since we wrote the position piece, I guess one version of that has been realized. So if you look at materials, one of the canonical problems is given the identity of a material, right? So say specified as the coordinates of the crystal structure. From there, can we map to any arbitrary materials property, right? Of course, we have a method by which we can do this, right, which is extraordinarily popular, density functional theory. But the magic is in having a functional that actually gives you the answer you want, right? And I think the general representation problem of finding the perfect exchange correlation functional has not yet been realized, right? And I think the ability with differentiable programming, which allows you directly to hopefully backpropagate all the way from the final answer, which we have very many good experiments, good higher order calculations, to be able to learn directly the exchange correlation functional, which I think will unlock being able to design all kinds of new materials for superconductivity, highly correlated problems. I think finding the exchange correlation functional is one North Star, and I think that's one avenue. The second avenue I think would be in the fluids world, which is to try and address the turbulence closure problem, right? To find newer representations, beyond whatever we can do with various kinds of other closure schemes that have been proposed. I think those are two really amazing problems where I think we can do amazing things in the sort of in the grand sort of challenge sense, like what protein folding has had. So I think those are two ways in which we can address this.
Other folks, David?
Yeah, I mean, I'm not sure we have to pick one problem. We just have to pick impactful problems. And I think, generally materials discovery, there's lots of impactful problems. We're developing, better solid state battery materials, better flow battery materials, better catalysts, better semiconductors. All those are great. I mean, trying to develop the ability to automatically design system topologies, I think would be very useful in lots of applications, electrical circuits, thermodynamic systems, even in molecules. So I would just focus on applications that are going to be critical to us going forward. I mean, climate and energy, I think, is certainly a big one, for example.
Other folks want to, Olga, Mark, Mike, thoughts on this?
I was just going to build off of David's comments. I think my perspective is similar to him in this way, is that we probably all come with our own personal, the way I describe it to my students is we have superpowers and supervillains. And so we've each got our own little supervillain that we care about, right? The new material or a new aircraft or whatever it might be. And then the superpower is the thing that's bringing us all here together at this particular venue, which is maybe the use of AI and machine learning and its associated really interesting pieces that all tie together. So I actually don't think we need like one North Star. Maybe we need like a couple of constellations, but maybe we all get together for lunch every year and talk about the superpower, because I think that's ultimately where we're going to reach out and hit the most sort of sets of impact. So I would just kind of further David's comments. I think we don't necessarily need to pick one, but having a couple that you can point to would be super helpful, especially for students, because I think, I'm a mechanical engineer by training. And so for a lot of us, when we say we do design, they say, oh, design what? Like a robotic cheetah or like a wind turbine? We say, no, design all the things. all the things. We design all the things. Like, we don't understand what that means. But if you can point to like 7 or 8 different challenge problems and say, you see this one technique that we developed for this one program, and see how it works for this, and then people all of a sudden start to see, oh, I see that investments in this technology have far-reaching value beyond just a robotic cheetah, for example. So I think that's sort of my perspective on that.
So maybe let me twist the answer slightly. So maybe we should think about changing the culture in terms of sharing the data, right? So many properties are correlated with each other, right? So if we change the culture, we share the data becomes open. It's easier to find the data, to actually ingest the data. Maybe it will be easier for us to solve all those big problems, right? So maybe the answer is not what problems to work, but like, how do we change our culture to share the data so that it's easier to find new materials, like at certain point.
Yeah, and that goes to the question of streamlining the field, right? So I think folks had I talked over someone, so please go ahead.
Okay.
I'm sorry. Go ahead, Mike.
I was just going to add one final thing, which I didn't hear before, is probably combinatorial optimization and using AI to improve those techniques in manufacturing, which, we see a few papers coming out of Google for chip design. And as soon as you solve that problem, then those are immediately applicable to, factory floor layout and scheduling, and pretty much anywhere you have a quadratic assignment problem or anything like that.
Excellent. So one of the questions in the chat is differentiable programming the only way, or are there other opportunities to explore, like non-differentiable techniques?
I think the answer is yes. There's certainly other techniques. Differentiable program is very powerful, and programming is powerful in itself, but there's certainly other ways to solve the problems that it solves.
Given I made a comment, I will of course concede to that statement. Right? Obviously, there are other ways to do it, but I think the thing that that excites me is to be able to differentiate through multiple programs and be able to chain gradients across like various software. I think this is a capability that honestly, like, is unimaginable in a different era, right? So like, I could write a Julia. Something in Julia, something in Jax, something in PyTorch, chain the gradients all the way, right? I mean, I think that's why I am just so optimistic about sort of the opportunities that's enabled by differentiability, but obviously lots of problems. There's nothing to back propagate, right? There's not enough information in the loss function to be able to send back. So clearly, there are other ways in which one should approach this.
So that, I mean, the theme that I'm seeing here is that there are perhaps a few North Stars, but like Mark said, there may be constellations rather than a North Star. So one thing that we heard through the day is that in contrast to, say, large data sets that are in genomics, in say astrophysics, design and manufacturing perhaps are characterized by smaller data sets and a lot more diverse applications. So thoughts on how do we leverage existing ML and AI know-how to advance our field, right? Is there value for, say, foundational models that we have been hearing about, or are they, I mean, we talked about benchmark data sets. Are there other things that, how do we leverage existing know-how, right? So,
well, I thought it was actually kind of neat today in Elizabeth's talk where they talked about using kind of these general CNN models in their materials characterization, and that they were great head starts. And if there's similar approaches we can take that reduce the amount of expensive data we need, that's certainly wonderful. And certainly just trying to figure out how to acquire the right data points rather than requiring reams and reams of not useful data or not impactful data, I think would be very important. And I was just I think to Olga's comment when she talked about the value of data, and it does seem like certainly within the differentiate program, open source data has been critical to a lot of the different projects, and it does seem like there's more and more effort to create and add to these open source databases, which I think are going to be resources for everybody. I mean, certainly there is proprietary nature to some of the data, but not all of it.
Other comments?
In terms of designing data sets, I certainly think in terms of like the production run model, where you can't really consider it all, one uniform distribution, and thinking of having a really well-trained model on a whole series of past production runs, and either seeing startup differences or just a systematic difference in a new production run, and being able to detect that really early in the production run is definitely one of the places where we've run into real world problems. So, and then also you have sort of that drift that starts when you first start a production run. So things that are very specific to that would be of interest to me.
I'll maybe add that. Oh, go ahead, Olga.
No, go ahead. You started first.
Okay, sure. I was going to suggest that maybe our greatest strength is also our greatest weakness, which is that, for a lot of interesting mechanical engineering, at least this is my field, applications, there's really fun properties of physics or science that we can leverage. So the standard example that I use a lot is space groups or invariant groups. For example, conservation of mass, momentum, all of our like conservation laws come down to a property being invariant under a very specific kind of geometry or group theory, for example. And that's fascinating, like really cool just in and of itself, right? Like Noether's theorem and all this other stuff. And then you think of people in the machine learning community who are looking at how do we do machine learning on space groups? And they have to come up with interesting examples of like rotations or tori or other types of things. And we have like those in spades. We've got so many of those, right? And it's just absolutely wonderful to like see that that's a strength that we can bring to the table. Like, let's look at a real world application where these really cool machine learning, fundamentals could inform practice in an impactful way. At the same time, I said it was a weakness, which is that by specializing a model in that way, I can show that I can get, order of magnitudes or two reduction in terms of the amount of training data if it's on a sphere, let's say, but only if it's on a sphere. And so we've got these in spades, like everybody has their own like special thing that they have for their own communities. And that's one of the things that's wonderful, I think, about the stuff that we do. But it's sometimes also limiting too, because if you have a technique that's specialized for that, it doesn't necessarily transfer in the same way that like a general architecture would for a wide variety of problems. So I think that's fascinating, but I could also see how some people would think of that as a potential weakness or drawback or as a stumbling block as well.
Mm-hmm. So to answer the question on like small data sets, right? So what if we have many small data sets? Maybe we should start thinking about methods that will help us to ask this question of generalizability, right? It already came up multiple times, right? But quite often we think about generalizability in terms of like cross-validation, right? I split my data. But maybe another type of question we should start asking, we have 2 or 3 different data sets, right? What are the metrics that will a priori allow us to say, okay, this model have a chance of like working for this data set, or maybe we should like look into model selection type of a problem, right? Because we will need to face at certain point problem of multiple different data sets, right? How do we integrate and like can we like push the ideas of generalizability across small data sets?
Yeah, and that essentially goes to a point. One of the members in the audience says that I think we have to, when we train the next generation of scientists, I guess we got to ensure that they have a clear vision of what the landscape of ML AI tools are, and not just what is currently hot, right? And then so I think that's an important takeaway, at least that we ought to do, right? So the question that I want to ask a few more questions on what Mike was talking about, right? So is there, how do you essentially look at where do we need more data and how much data do we need, right? Especially in this off corner cases, right? So can you, from the industrial science perspective, right? So can you talk a little bit about that, Mike? And then I'll ask Venkat the same question from a startup perspective, and then Dave from the funders perspective.
So from the manufacturing floor perspective, we've got one more advantage, which is, it's not like we're looking at an entire wide range of images like ImageNet. We're looking at really repetitive images, and templates actually do work quite well in a lot of these settings. And then the question becomes, do you have a template method with deep learning on top of it, just looking at the deltas off of that template, or other deterministic or physical models? I liked the group theory passage that Mark was talking about. I was originally a mathematician, so I'd be interested in hearing more on that. But a lot of this comes down to sort of, we've got a setup where we have less data, but we also are probably in a good position to use less data, just because the images that, or the data that we're looking at, tends to have a lot less variation than sort of in the wild data sets. But then there tend to be these sort of very strong sort of patterns or state changes that you see in that data, and you won't necessarily know what those state changes are going to look like ahead of time. So there's a lot of like one-shot and low-shot learning that applies as well.
I mean, from my perspective, I mean, less data certainly is very important, but sometimes even having a guesstimate of how much data we're going to need to develop a capability before we decide to do it would be wonderful. But I'm not even sure that problem is necessarily knowable or calculable before we start. And I guess I'd be interested if anybody has any thoughts on that.
Yeah, so maybe I can share some perspectives of what we've seen work at AAAI. So AAAI is a company that offers machine learning informatics solutions for the energy storage space. So we work with a number of clients that exactly try to answer this question, right? How much data, how much should we sort of spend as a data collection period before we go off and like discover the new material or new functionality and things like that. And of course, we worked on a variety of different design spaces in the energy space, being making polymer, making ceramics, making liquid components, and so on. And of course, the answer is always it depends. But I think knowing that the answer is it depends actually already sets you on a path to succeed, because then you can set these metrics at the beginning, saying if your model is of this accuracy, then we can start to sort of forecast forward. And being aware of these issues, I think is the main sort of learning that we've had. And of course, I think this goes back to sort of the impact and value and calibrating the value, right? I think it's really important that we set the expectation that you can only achieve so much, right? It's not going to substitute for you thinking and defining your design space efficiently. And I think one thing that is underappreciated is design space quality, which I think I would credit Citrine for sort of really pushing this forward in the materials community. It doesn't matter how good your data collection scheme is, how good your models are, if your original design space over which you're searching is bad, right? So no amount of data collection and models is going to solve that problem for you. So I think finding ways to do good design space quality assessment, in addition to I think all of the things that we talked about, I think that's what really helps on the field, I would say.
Yeah, I think a lot of people try to use statistical methods for determining, what your data set size should be in deep learning. And I think there's a problem there, which is that, deep learning is at least as much compression as it is statistics. And so if you were, the minimum data set size should be something that could test a compression algorithm is beyond just a statistical test.
So are there other avenues for value creation here? One thing that Venkat pointed out too is, can we frame and understand the design space in which we're working through it? And that's that does make a lot of sense from the value creation. Other points, I mean, and this is, I'm going to again poke on David from a funder's perspective, right? So what do you envision from a value creation perspective?
Well, I mean, I guess from my perspective, we want to design better energy products faster and better, more efficient tools, I think, enable that. I guess I'm not sure I really understood your question. And so anything we can do to enable energy engineers to be more productive and come up with better ideas and evaluate them faster is success.
Maybe I can try to take a crack at this answer, Bhaskar. I think the way you're thinking about it, right, is I think it's clear, Dave, right, that you can you're creating value. The question is, how do you capture the value, right? So we run into this issue at AAAI Onyx all the time, right? We can bring down the number of iterations by a factor of 10, all these things, right? So how do I extract money from the client for that unlock, right? And sort of how do I sort of really, I think, capture beyond the sort of conventional models for like just pay for compute or licenses, right? I think drug discovery has started to unlock some of these models where the pace of innovation is captured, either through milestone payments or sort of capturing how much experiments you have reduced relative to sort of baseline. I think going through this process and like demonstrating, I think in differentiate, I think many teams have demonstrated the success of these methods, but I think having I think going that next step and demonstrating how much did it actually save in a particular project is, I think, non-trivial to demonstrate.
It is. I agree with that completely. I've asked 23 times at least, and probably much more than that. And I'm sure you guys are sick of hearing it, but yeah, it's a very difficult question to answer. I mean,
maybe I'll chime in because I think I center on this question earlier, so I explain my thinking. If you look at the trajectory of, say, computer vision over the last decade. And the performance has been steadily improving. We've seen the growth of better models from AlexNet all the way to now, right? So it's about a decade of growth, and people have done all kinds of things, right? Like throw in their favorite model, their favorite optimizer, their patch normalization, whatever, right? Like throw in their favorite idea, conceptual idea. But the one sort of determining factor has been data set size. Right? Like regardless of what architecture you use, stuff like that, like if you plot time versus data, and so if you correlate data set size with performance, it's like a straight line, right? Like or log of data set size versus log of performance, right? So which suggests that if we were to achieve the same kind of advances in, say, material science or materials design or manufacturing, we just focus on getting more data, right? Like just increasing the ability to process more data, right? So that was the thinking, right? So what do you think is the sort of best bang for buck in terms of?
I mean, I think that's a great point. More data is certainly would be a wonderful thing, but actually, I think a lot of the investments that we're making is to try to minimize the amount of data that we need by making the right choices in terms of the models that we have. Structuring the networks in such a way that it minimizes the number of weights that we have to train, minimizes the amount of data. Are there rules or physics that constraints we can impose on the problem that make the problem simpler, which reduce the amount of data that we need? I mean, I agree, more data is always a good thing, but unfortunately data is very expensive. And so a lot of the effort has been to try and reduce the amount that we need by imposing these constraints, as I mentioned.
Yes. At least for me, it's usually a lot easier for me to generate a return on investment story for a materials design or a change in a manufacturing process ahead of time than for metrics that are trying to sort of save you while you're in the middle of a production run. Because by the time you get an answer, you may be done. So that's definitely an easier path for me to justify.
to say one interesting, we've been having folks develop these combinatorial optimization approaches for designing things like electrical circuits. If I have, a resistor, capacitors, inductors, MOSFETs on a bench, how do I combine those to convert electricity from one voltage to another? And, if you restrict it to maybe, between 5 and 10 different components, it turns out that, like 98% of the potential combinations you put together are really bad ideas. And only a couple percent actually have a chance of working. And so the question is, are there, but the problem is it's expensive to evaluate all those really bad concepts, but are there simple rules that we as engineers have learned that says, don't connect the input directly to the output? That's a short circuit. That's a really bad idea, which eliminates a large fraction of the design space. And are there rules that we can impose that would basically simplify the problem to the point where it actually becomes more addressable with our ML tools, reducing the amount of simulations that we need and the cost of data?
Yes, so one area of interest for us is definitely explainable AI for reinforcement learning, because for that exact point, because we're using reinforcement learning for the most part for those combinatorial optimization problems. And if you can have it's not even having a true explanation, it's just putting it into the language of the designer. The decisions that are being made internal to the network, what are those closest to in terms of rule sets that a designer would have?
Yeah, go ahead.
Go ahead. Yeah.
I was gonna say, that's a great point. Actually, we have some folks that are trying to do that as well in RL algorithms. And can you have the algorithm make a decision and spit out a rationale for the decision at the same time? And it's certainly a non-trivial problem.
So can we talk a little bit more about that in terms of what are barriers to adoption, right? So, there's, you talked about this notion of explainability. And earlier today, we had a discussion about, do we only care about a prediction accuracy, or do we actually care about insight and pushing the science envelope, right? And so there are different, essentially a Pareto front there, if you will, right? So can folks talk about that and talk about what are the barriers and how important are some of the features that we look for in ML?
I remember at the workshop we had to kick off the Differentiate program, we talked about this issue a little bit, and everybody agreed that trust was absolutely critical. You have to believe the algorithm is going to do what you expect it to do, and it's going to do that. Things like explainability, there was much more debate. And there's some folks that argue that it's certainly a nice to have, but there's lots of processes that we have today we really don't understand, but they seem to work, and so we do it. And why that makes us less comfortable, it is sometimes acceptable not to actually understand why something works the way it does.
Yeah, one metric I like to use in that space is what is the price I'm paying for the explainability or the trust,
right.
i.e., like how much are we losing in correct decisions in test for that added feature? For the most part, it seems like it's not very much.
I'll make a controversial point here, but explainability is dimensionality reduction to the knowledge space of the person that you're trying to explain to. And that's a dimensionality reduction that you probably don't want to do.
Depends on the person. No.
Yeah, I have been mixed on this. Obviously, I am deeply rooted in physics. So I think explaining and understanding and interpreting is crucial. But I think the way that term is used in the context of all of these discussions is largely, it's simply a projection of whatever answer you get to the human knowledge space, which may or may not be the right way you want to think about these high dimensional representations. So
maybe to counter Venkat's controversial view with a absolutely not controversial view, I'll say it depends a lot in that, you know, like, for example, the circuit case that David, you know, mentioned, you know, we're doing that for Lens, and there, you know, they kind of don't care as much if we can explain what's happening, as long as the designs are better than the humans, you know. I mean, it'd be nice if there was some explainability, but that's not the top line result. Whereas we have another NIH project where we're like recommending heart grafts for surgeons to implant in newborn children. And if we give them a design that's different than what the surgeon had in mind, we better have a pretty good reason for why that heart graft's going to be put in the child, right? And so I think it just, you know, very much depends on the application, and you know, that's why I think this kind of explainability or not is kind of to Mike's point. You know, it's what's the return on the explainability, and for many fields it's a lot, and for some it's not. And I think that's a lot of fun for us, because we get to have a lot of, you know, time explaining that to people and exploring that.
So is there, I mean, one thing that as I work with a lot of experimental material scientists, I mean, they have very exciting, challenging problems where ML approaches can be brought to bear. However, it's been, at least personally, it's been a struggle to get them to adopt some of these things. They understand the value, they think it's magic dust, sprinkle it on it and solve the problem. But getting them to adopt has been a challenge. And so Olga has been at the forefront of some of these things, right? She's part of MARDA, the Material Design Alliance. So Olga, do you want to talk a little bit about what the challenges are and what we could do as part of the connecting part of the Venn diagram with AI and materials, right? So
I wanted to say something about the risk, right? I think the fields where AI was like very successful, or in general data-driven or high throughput explorations, are where we are hopeless, right? And I think if you don't have a good physics-based models, right, then you are more willing to adopt solutions that are not necessarily commonly used, right? So I think maybe it's not about the trust, but like ability to take a risk. Right, so early adopters of like high throughput explorations, those were like pharmaceutical companies. They just like didn't know what to do, so they could afford, so they did it, right? So maybe it is more about risk taking. Those are the fields that will adopt earlier.
interesting. So I think we are almost at the coming to the close of our session, but maybe we have a sort of parting thoughts on key takeaways to both the AI community as well as the design and manufacturing community that folks want to state.
Well, I guess I would just say, you know, we're looking for ideas about where to take the technologies we're developing within Differentiate next. And if you've got ideas about where we think we should go, technology investment opportunities in the ML for design and manufacturing space, please let us know. We're all ears.
I can go next.
Please go ahead.
Okay. Yeah, I was just going to say, I appreciate, you know, I think one of the things that's really great about what you've done here, you know, with the workshop is just the bringing together of people on the superpower and supervillain side to work through this. I'll make two kind of shameless plugs that may benefit people here. One is that we are assembling sort of, I'm not going to say too much about it, but in later this year, we'll be releasing things that could, I think, address some of the problems that people have here in terms of wider scale problems and data sets that we could work on together. So if anybody would like information on that in June when that comes out, here's where you can enter your email, and I'll send you an email when the GitHub link is available to you. The other thing I'll mention is if you have students who want to learn some more about this. So for example, things like the group theory stuff that I mentioned, as part of my career proposal and a separate NSF grant, we have a summer school that's going to be this summer for anybody who wants to learn design plus ML that's doing kind of new areas of mathematics, including information geometry. So if you do have any students who are interested in that, you can take a look at this link. You can enter your email and I'll send your student students their registration. It's a really fun time to come out, all expenses paid to College Park for any students who are interested in partaking. And if you're a faculty member or a research scientist who wants to take part in our kind of writing group in the mountains a couple of weeks ahead of time, you can also enter your information there. So those are just two shameless plugs, but I'd like to keep the community conversation going, since I think this is really exciting. And this wasn't around when I was starting as a faculty member, you know, like a half decade ago. So I'm really excited to see it now, because I wish I had this when I was starting out.
Okay, following on Mark's shameless plug, I'll also do a shameless plug. I think similar to, I think, what Mark was saying, we run this scientific machine learning webinar series, which actually Dave was kind enough to support some of that in the early days within our Differentiate program. We've actually touched on many of these topics. We get through different themes. And so we did one where we addressed symmetries, symmetries and sort of machine learning, addressing some of these questions around geometric deep learning. To me, the parting thought is, I think, should I go back or maybe should I just go and sit in Mark's summer school and take the group theory that I didn't take during undergrad? And is the geometric deep learning going to win out? Or can I just live with the fact that, okay, I knew my physics and now I can just differentiate through it? You know, which of these two camps is going to win? Or maybe it's a fusion. I think that's, to me, the exciting frontier. And thanks for organizing this. This has been great.
Thank you very much.
Other folks, final thoughts?
Sure. I'm so glad that the end of this turned into a math discussion. A couple of other things you might want to look at are topological data analysis. And there are some other techniques. I guess I'll have to look them up offline, but there are a lot more techniques trying to constrain the geometry of latent space, so that, you know, rather than trying to apply some metric after the fact in latent space, you constrain the geometry during training so that it's explainable. And I hope Venkat doesn't get angry at that.
Olga, your final thoughts?
So I would echo what Brian said, right? In terms of like data curation or how much data do we need? Like success of machine learning depends like majority on the data, right? How do we prepare? And those who did like training, they know that most of the times we spend on like data, cleaning, preparation, merging, and so on. 30% is featurization and 10% is models. So like from the practice perspective, like that's like more or less the vision. Brian said like 60 and 40, I guess that's the vision in terms of like what we complain about, right? So maybe we should like think more about like what do we do with our data, right? How do we collect data? How do we clean? How do we share the data? So those are like my final thoughts.
Thanks. And at this point, I'm going to hand over to Chinmay, who will close out the workshop. Again, thanks everyone for this wonderful talk.
Thank you very much.
Awesome.
Thanks.
So 7:49 p.m. on the East Coast. I just want to close by thanking everybody. I think it's been a wonderful several hours, and I hope all of us learned quite a bit. I certainly did. And I appreciate all the speakers, all panelists, all the organizers, and particular shout out to two people who did a lot of the work, and that's Bernard and Aditya. So kudos to both of them. So with that, I have the background behind me. I'm sorry that we couldn't meet in person, but hopefully the next time we meet, it will be a real conference and we can continue this conversation in flesh and blood. Thanks so much. And with that, we'll see you all. Take care.
Bye. Thank you. Bye.
Thank you very much.